Our next speaker is Russell Hendel, who will talk about the title of his talk.
Yes, I'll talk about the title of my talk, which I'll explain. Um, First, I'd like to thank Mel. Most people thank Mel for hosting the conference. This is being presented at three conferences. The International Fibonacci Conference gave me 12 minutes. The International Congress of Mathematicians gave me 20 minutes. Mel's giving me 25 minutes. So I really appreciate the opportunity to give the full story here. Okay. I'm going to start by telling you what the Laplacian, I assume everyone knows what a graph is, though it's in the slides. The Laplacian is a matrix associated with a graph. Let's look at this graph. In the cell 1, 1, row 1, column 1 will have a 2 because the degree of vertex 1 is 2. In the cell in row 1, column 2, we will have a -1, and similarly in the cell in row 1, column 3, we'll have a -1 because 1 and 2 are adjacent and 1 and 3 are adjacent. In the cell in row 1, column 4, we'll have a 0 because there's no adjacency. So just remember those numbers, 2, -1, -1, 0. And there's the first row. It's degrees down the diagonal and adjacencies indicated by -1 or lack of adjacencies by 0. Okay, that's what the Laplacian is. Why should anyone care about it? And if you do care about it, how do you compute it? And if you care about it and want to compute it, what am I going to contribute? So the reason the Laplacian is important, one reason, is determinants related to Laplacian can be used to measure effective resistance. Effective resistance is a metric. It measures the ease of commute between two vertices in a network. Think to parallel circuits. If you have a parallel circuit, one of the parallel lines breaks, you have the other one. So everyone studying connectivity is interested. Social networks, biological networks, ecological networks, and transportation networks. It's also useful in chemistry and lots of other applications. Evans and Hendel, in a recent issue of the Fibonacci Quarterly, published this year, gave an overview of it. How do you compute it? First, it's been computed for many graph families. They're listed there. There are about 40 of them, I think. There are many approaches for computation, electric circuit methods, combinatoric, graph theoretic, numerical, and recursive. A very good reference for the linear algebra is Bappett's book, and a good reference for an overview of the computational methods is a paper by Evans and Francis in Discrete Mathematics, published in 2022. So what am I doing? I am contributing to the recursive methods for computing the determinants associated with the Laplacian. Here's the history. Before 2015, no one used recursive methods. I mean, they used them, but they were ad hoc. In 2015, Jia, Yang, and Li published a paper using Laplace expansions, and to echo what was just said in the previous lecture, very elementary method. They obtained the recursion satisfied by the determinants of the family of Laplacians of pentadiagonal Toeplitz matrices. It's an order 6 recursion, and they used that to compute anything they wanted. And as they note in the paper, if you have Binet forms and hence are computing with powers, your speed is increased by 70%. They didn't give a method systematically for expanding the Laplace expansion. So Evans and Hendel, in a paper accepted in 2025 to appear in the Fibonacci Quarterly, developed a method. They used it to prove the linear 3-tree conjecture, and it has a 14th order recursion, but the method we did proves it. The method is potentially generalizable, but we could not prove that it works, that it always converges. It worked in that particular case. So what I'm doing today is showing that a particular Laplace expansion method, paradoxically, which is simpler than the one used by Evans and Hendel, works, and I'll prove convergence. Okay, after some notational conventions, I will give you a very simple example and spend about 4 minutes on the next slide. M is a size n matrix. If A and B are sets of indices, A semicolon BM is a matrix obtain from M what the rows indicated by A and the columns indicated by B deleted. So if you think of a Laplace expansion, you want to delete one row and column. Now, there are possible problems here, but I'll come to that later. So here's an example. A3 is the size 3 matrix of the family of tridiagonal matrices. You see there are 3 diagonals here, the A, B, and 0. A2 is the size 2 matrix. If I expand A3 using Laplace expansion on the first row, I get the determinant of A3 is A times some determinant minus B times some determinant. If I eliminate row 1 and column 1, we see we get A2. And that's a general rule. If you go to a Toeplitz matrix, which means its diagonals are uniform, and eliminate the first n rows and n columns, you'll get another matrix in the same family. If I eliminate the first row and second column, I get BB0A, which is B2 here, and B3 is just the size 3 matrix in that family. So this is the equation we have. Determinant A3 is A determinant A2 minus B determinant B2. Here's the problem. I want to do this all over the place. And the left-hand side has matrices of size 3. The right-hand side has matrices of size 2. If I keep on doing this, I'll run into degeneracy problems. So I'm going to use the backward shift operator. The backward shift operator takes the element determinant A3, a member of the sequence of determinant AN, and gives me back determinant A2. Similarly, the backward shift operator applied to B3 gives me B2. So I get this equation, which is equivalent to that equation, but look what's going on here. The sizes of all the matrices here are the same. So I get a statement in the family of matrices. Determinant of A is AY determinant A minus BY determinant B. That will be true wherever all matrices are defined for that size n. Now, I just want to finish this by expanding B3. We have a B here. Well, it's a diagonal matrix. I eliminate the first row and first column, and lo and behold, I see my friend A2 here. So determinant B3 is B determinant A2, which, as we explained before, is B times the backward shift operator times A3. So I get these two equations, which we'll see in a second. Determinant A is AY determinant A minus BY determinant B, and determinant B is BY determinant A. Before I show you how this gives us the recursion, let me just go over 3 approaches. Jia, Yang, and Li just gave an expansion, and it worked. Evans and Hendel suggested expanding by the first row or column, check for transpose, see if you've seen this matrix family before. We had to manually check for encountered matrix families. We wrote some software which is available on archive. We could not prove convergence. So in this presentation, I'm going to change the method. I'm going to expand by the first row until there's one last expansion where the first column has one non-zero entry. I'll then expand by the first column. I will algebraically check for encountered families, and I will prove convergence. So these are the equations we have. Let's look at what we can do with them. This is by the first row. When you expand by the first row, you get this equation. When you expand by the first column, you get that equation. I could plug the second equation into the first equation and get that equation, right? BY times determinant B is BY times BY determinant A, which is that. I can then gather terms, so I have an operator times determinant A equals 0. What does that mean? That means if you apply this operator to any to the sequence of determinant AN, you will always get 0. That means I've found the recursion or the characteristic polynomial. All I have to do is solve this equation. I get roots, Binet forms, and I can compute whatever I have to. It's left to prove convergence. So I'm going to give 3 prerequisites. First of all, I'm going to deal with repeated first row expansions because we keep on doing things by the first row. Let's look at the bottom equation here. I remove row 1, column 1 of the matrix A. Then I remove row 1, column 1. Operators go from the inside out, from the right to the left. Then I remove row 1, column 1 from the resulting matrix. Then I remove row 1, column 1 from the resulting matrix. What have I done? I've removed the first 3 rows and the first 3 columns. So that's an algebraic relationship. We don't have to manually check everything. Now I'm going to do some more with sequences of operators. Supposing I remove row 1, column 1 from M, then row 1, column 1 from the resulting matrix, then row 2, column 1 from that matrix. I contend I've removed the first 3 rows and columns 1, 2, and 4. Why the first 3 rows? Because I've removed the 1 here means I'm removing the first row. The 1, 1, and 2 means I'm removing the first row, and then the first remaining row, which is, the first column, the first remaining column, which is column 2, and the second remaining column, which is column 4. And if I remove the first 2 rows and 2 columns, I get back a matrix in the family. So I'm left with the third and fourth column, but I've eliminated the first 2 rows. So I get this sequence of operators is equal to this is equal to 1, 2m. And again, that equation is true where everything is well defined. So this will be defined for all matrices. This will be defined for matrices of size at least 3 or 4. So those are examples of how sequence of operators can lead to an algebra of operators, and you don't have to manually check things. Finally, I have to recognize when I've previously accounted a matrix. If you remember here at the crucial step, I had to recognize that when I eliminate the first row and first column, I get back A2. In other words, I recognize this ABBA as a formally encountered matrix. What can I say in general about that? So we have an original matrix family M, current expansion step is K. Each of the K expansions are along the first row. Let's say I call the matrix A semicolon B M. What can I say? Well, I've removed the first row K time, so A means remove the first K rows. What about B? B will consist of a sequence of columns eliminated, and they'll all be between 2 and r plus k minus 1. The converse of this is true. If you give me an MK, A, and B with this property, I will construct operators, a constructive proof, such K operations that will give me back AB. So I can completely describe matrices encountered. So now I can give you a high-level overview and then a more detailed overview, because as I said, I have 25 minutes. I'm given a family of tuplets, and this is the proof. What am I proving? I'm proving that this procedure, expand along the first row until you're left with a column with one element, then expand along it, converges. That is to say, there'll be no new matrix families added. You'll have a system of equations in determinants and families, and you can solve that to get the Binet form. The method of solving determinant families is just by elimination, and it was given in the paper of Evans and Hendel. That will be published, I believe, this year. Okay, you're given a family of tuplets matrices, and we suppose all non-zero items are in the first column of M. In the case we looked at, R was 3. On step 1 and subsequent steps, expand matrices on the first row. At step R minus 1, I've deleted the top R minus 1 rows. Let's say I'm left with A semicolon BM. The first column has one non-zero entry left. It's a diagonal matrix. So I'm expanding 1, 1, AB. I get A prime, B prime. And the point is A prime, B prime, I can recognize it because whenever I have a row 1, column 1, or 1, 2, 1, 2, or 1, 2, 3, 1, 2, 3, I'm shrinking the size and reducing it. And if I'm reducing it, beforehand, I had a sequence of a sequence of items sandwiched between 2 items. And now I will also have that. So it was previously encountered. So there are no new matrix families, and I have convergence. I'll just go over that in a little bit more detail because I have the 25 minutes and I have time for questions. So again, I start with the matrix family, say M, expand along the first row at each step. I'm going to reduce the sequence of operators, which means applying those algebraic operations to simplify it. I will recognize previously encountered matrix families using that lemma, and I'm going to store the resulting equation. At the initial step, I expand along the first row, and the first column has one non-zero entry. I'll expand along the first column. Let's look at that a little bit more in detail. At that step, I started with A semicolon BM. That means I deleted the rows in A and the columns in B from M. Now I'm expanding along the first row, first column, so I'm eliminating the first row and first column. Well, A and B did not, so what I'm basically doing, I'm looking at 1 comma A and 1 comma B. and what that is, it's reducible because I'm going to shrink it by the size, because when I remove the first row and first column, I get a topocyte matrix. So the completion of the proof in each B is monotonely increasing set of numbers with certain bounds. So if I reduce it, its reduction is also monotonely increasing. And by that lemma was previously encountered, I have to check on the maximum and minimum. That's not a problem, but it has to be done. We have no new matrix families, no more equations, and the process has converged. This is the statement of the theorem, which we just proved, that M be an arbitrary banded square family of Toeplitz matrices of Toeplitz order R greater than 2, where the Toeplitz order is how many non-zero elements are, let's say, in the first row or the first column, or how many diagonals are not zero. The expand procedure, which we just gave before, terminates after R expansions. And using the techniques of elimination by substitution and operator multiplication, which I showed you for the case of the R equals 2 family, the tridiagonal matrix, the solution to the resulting set of equations and families of determinants can then be solved to yield a recursion satisfied by this family. And as I said, Evans and I, using this, applied it to the family of linear 3 trees. We found several order 14, there was an order 14 recursion in the numerator and an order 5 recursion denominator. And lo and behold, they had explicit algebraic roots. We could get the dominant roots. We can compute asymptocities. And we confirmed what the linear 3 tree conjecture stated. And then, as my collaborator Evans reminded me, Russell, you've only proven the K equals 3 case. The conjecture was for all K. So we haven't done the other K. And these are the references. I mentioned Bappert, I mentioned Evans and Francis, and I mentioned the introductory survey, which is a good paper to read if you're interested in this. This is to appear, and there's an archive version. This paper is in review by the Fibonacci Quarterly in a special issue dedicated to Curtis Cooper and to Benjamin, the previous president of the Fibonacci Quarterly. This is the paper of Jia, Yang, and Lee, which appeared in Computer Journal. And now I have room for, I can have questions and anything else you wish to add.
Thank you, Russell. Any questions for our speaker? If not, I thank Russell again. And you didn't even use your full 25 minutes. Wow. Okay.
No, but I had to truncate this when I spoke 12 minutes. And that was...
That's fine. That's fine.
I'm really happy I could go through the whole proof. And as I said, I was happy. And it's an interesting technique. I hope it's used. I hope it's used to solve other conjectures.